Here we are with a lesson on speed and velocity. So we're talking about a couple different things today, and I'm going to break this lesson up into two smaller parts. So first and foremost, a position time graph is of course a graphical description of motion. And so what we're going to see over the course of the next few days is that we can use position time graphs to get lots and lots of information. Very specifically, the slope of a position time graph is the velocity of the object that's being graphed. And certainly we're going to see that speed and velocity, just like distance and displacement, they're similar, but they're very distinct characteristics. Okay, so this is what we're going to talk about today. Our first item of note is something called average speed. And so really, for some object in motion, we define speed, and specifically average speed, as the total distance that traveled divided by the total time that's elapsed. And so we have a formula here, and you'll notice that these are not vectors, these are scalar quantities. So speed, and you'll notice there are no vector hats. This speed is equal to total distance over total time. Okay, and we'll keep that in the back of our in our back pocket, because we're going to come to a couple examples later where we're going to use this. All right, so continuing, let's talk about position time graphs and kind of what they're all about. So yes, I know that there's already a lot of writing on here. Don't fret. I'm going to highlight as you go. Press pause if you need to kind of copy something out. But what you'll notice certainly right away is that we have a position time graph for a toy car. On the one axis, we've got our displacement, or our position rather. It's measured in units of meters, and the positive axis is in the east direction, and we've got down here our time axis, which is measured in seconds. So if you were to read this graph, of course what you would find is that you would find instantaneous values of the object's position. Okay, and what that means is that for every instant, that's why we say instantaneous, so for every instant in time, you can find a value for this object's position. Okay, which means that if you come down here and you say, okay, at 4 seconds, I'm going to look up to the graph here, and then I'm going to look over, and I see, okay, that's roughly about 21 meters is its position at 4 seconds. And we could do that for every single instant in time that we've graphed. Here's another example. At 6 seconds, the toy car has a position of 27 meters east. Okay, so this is what we get when we read this graph, lots of information. And now we're going to focus our attention on finding the slope of this graph, right? So just remember that, of course, slope is equal to rise over run. And in this case, instead of saying y2 minus y1 over x2 minus x1, which is a very common and familiar equation for slope, we say, well, we don't have y's and x's, we've got d's and t's. So we got position 2 minus position 1 over time 2 minus time 1. And you can see in my diagram here, I've indicated 0.2 and I've indicated 0.1. You could have picked any two spots on the line, doesn't really matter. But I've got 30 minus 10 over 7 minus 0, which gives me 20 over 7, and that's about 2.86 meters per second in the east direction. Now, meters per second, that's distance per time, that kind of gives us a hint as to what the slope of a velocity time graph or of a displacement time graph represents, and that is the average velocity. Okay, so here you'll notice that we have vector hats, so this is a little bit different. It looks very similar to the equation that we had above. However, average velocity is displacement over time, right? You'll notice that this is position 2 minus position 1. This is what we call delta D, right? So this is delta D, which is displacement, and this is of course time. And so really when we find the slope of a position time graph, we're finding its velocity. We're finding information about its velocity. Okay, so let's take a look at an example here. A Lego train moves 1.25 meters east and then 0.75 meters west along its track in 8 seconds. Determine the average speed and the average velocity of the train. So we kind of know a couple things here. We're not delving quite into graphs quite yet, but we know a couple things here. And so here's what we have. So we know the time, it's 8 seconds. We know the first displacement the train makes is 1.25 meters east. We know the second displacement the train makes is 0.75 meters west. We want to know the average speed and we want to know the average velocity. So I'm going to do the velocity first, and then I'll come back to the speed. So here we have a vector diagram. Okay, so this is kind of like a diagram where I've shown in the first segment we started here and we went on a displacement that was in the east direction. Okay, and it was 1.25 meters. And then once we got there, we then moved back 0.75 meters west. So we started going one way, turned around, went the other way, all on this train. And so what we end up with is this right here, this little number right here is our overall. So this little bit that's in red, this delta dt, that's our overall down here. Is our overall. So we need to find out what that is. Of course, how do you add two displacements? Well, we know that to add two displacements, we simply add these two vectors, right? So we've got delta D total is equal to displacement 1 plus displacement 2. Kind of worked on this in class. And so what we have is we have 1.25 meters east plus 0.75 meters west. We know that this west is going to turn this plus sign into a negative, right? So we get this, because of course west in our general sign convention is the negative direction. And so what we end up with is 0.5 meters east as an answer. So once we know the displacement, the total displacement that the train makes, we can say, hey, wait a second, the average velocity is equal to displacement over time. So we get 0.5 meters east divided by 8 seconds, and we get 0.063 meters per second east as our average velocity. We can also come over here and we can say, hey, wait a second, what was the total distance that this train traveled? Well, it went 1.25 meters and then it went another 0.75 meters. Who cares about direction? So it actually went 2 meters in 8 seconds, which turns out to be 0.25 meters per second. You can tell that, of course, the velocity is not the same as the speed, and that is very often the case because displacement and distance are two very different things. Okay, so moving on, let's do another example, but let's do another example where we've got position versus time in the form of a graph. So consider the position time graph shown, determine the position of the motorcycle at 6 seconds, and its average velocity during the time segment shown. So one of the things that I'm going to do right now is we're only going to talk about this time segment. So we're going to talk about from 0 to 4 seconds. So this whole time segment in here, that's what we want to find. So first of all, the position of the motorcycle at 6 seconds. Well, we come over here and we say, okay, well, here's 6 seconds. And so what we're going to do is that we're going to track up and we get to this dot here, and then we track over and we see that's approximately halfway in between 200 and 250, and so we say its position at 6 seconds, so this is D sub 6, is about 225 meters east. Okay, so that's all I did. I just read the graph. And then if I want to do the velocity during the first 4 seconds, I'm going to pick 2 points. I need to find the slope of that line. So I'm going to pick any 2 points. It so turns out that I've chosen the first and I've chosen the last because those are very well defined points. And so I got 150 minus 0 over 4 minus 0, and I get 37.5 meters per second east would be the average velocity. All right, that's it for the first part. Take a break. We're going to go on to the second part momentarily.